Great question for the forum. Yeah, please ask questions like this on the forum. But we'll have instructions about that soon. All right, any questions about today's lesson? So today's lesson is on one particular implementation of a list. So we introduced Java's built-in list last time, and then today what we're doing is actually showing you how to build one yourself. So this is different than the array list implementation. It doesn't have certain optimizations that Java's official one does, but on some level it's very similar. It's an implementation of a list that stores the items in an array internally. So yesterday's homework, you did get and set, which were pretty straightforward when you're using an array. The next implementation we'll look at when we use a linked list actually is quite a bit different. And that one, get and set, will be a little bit trickier. But for an array list, get and set are just sort of array operations on that private array that you're maintaining. And then today's lesson, we go through how to do remove, which is more complicated because I actually need to change the size of the array. So this is one of those lessons that's mainly, kind of covered pretty well in the walkthrough. So I don't want to sort of scoop it. But I'll be happy to take questions. I know that this is probably, we're sort of going back and picking up our work on imperative programming. This is probably some of the more complex imperative programming that we've seen recently. So questions about this content, or maybe we'll give it like 15-20 minutes for questions about array lists, and then we can go back and talk about the MP if you guys want to talk about that. But let's take some questions on lists first. So any questions on this topic before we go on? Yeah, great question. So the wrapper is this object class. So if we look at the beginnings of our implementation here, I have this private variable values. That's where the data is actually being stored. The class. You could just use an array. You can use those in Java. They're built in. Why would I create this simple array list? This simple array list class? And the idea is that on some level right now, it's acting as a wrapper around an array. I just have these get and set methods. Once I start to implement add and remove, what we're doing now is we're actually writing code that arrays don't already support. So arrays already directly support indexing. So I can already implement, essentially if you look at get and set, which you guys did for homework yesterday, these are, there's an assertion and then there's an array operation. So there's no real reason at this point to use this simple array list class. I might as well just use an array. It's not doing anything new. Let's put it that way. It's not adding any capabilities that an array doesn't already have. Arrays already have these index operations, so why would I use this class? Once we get to remove and add, now, it's sort of like difference between an array and a list, right? An array, is a linear data structure, supports indexing, associates each value in the array with this piece of metadata, which is the array index. But doesn't have the ability to change size. So I can't add or remove elements to it after it's created. It's a fixed size. Lists, on the other hand, we want to have that capability. So when we look at this interface that we're implementing with an array, and then we're going to implement it again tomorrow in a different way, the interface has these two new methods, right? So get and set, at least for this implementation, are fairly straightforward because they just map down onto array operations. But add and remove are things that I'm going to have to do more work to finish. So, in order to remove something, I actually, because underneath, what I'm doing, how I'm actually storing the data is in this array. The array doesn't have a remove operation. So I need to find a way to add that myself. Same thing with add. So those are capabilities that we're augmenting the array class to have, right? On the other hand, again, so come back and maybe think about this again in a couple of days, because what we're doing right now is we're kind of doing the most straightforward implementation of a list, which is take the built-in Java data structure that most closely does what we already want, which is an array, and then just add these extra features to it that arrays don't have. Tomorrow, and a little bit of Friday, we'll look at a way to use a completely different approach to storing the data in a list. So we can actually implement this list interface, get, set, remove, and add, without using an array at all. There's another way to do this, and so we'll look at that next time. That other approach conforms or implements the same interface, right? It implements get, set, add, and remove, just the way that our array list class does. And the two can be used interchangeably. But internally, the way that they represent information is different, and there are some performance trade-offs between them as well that we'll look into on Friday. Our new language. Just a dynamic array, no linkage. It's a good question. I mean, so the question is, are new languages replacing classical arrays with lists? It depends. It depends on what the language is for. So for example, languages that are designed to support higher level programming, frequently there's really no reason. So the real reason to use an array is for performance reasons. So arrays have very fast lookups, and they're also very compact in memory. However, the fact that they're compact in memory makes it hard to support list-like operations like add and remove, because I have to do all this copying. So you can, in certain cases, by using an array and controlling the memory layout more carefully, you can actually improve performance a little bit. And so if you look at, different programming languages, something like Python, for example, Python lists are lists. I mean, Python really has no array type. It has a list. Those lists can change size and stuff like that. Now, internally, I'm sure that the Python list implementation is doing a lot of things carefully to try to achieve the best performance. But at the end of the day, if you're going to allow people to insert stuff into the middle, so you think about arrays essentially an array is laid out in memory in consecutive, so there's some portion of memory that contains the array. If I want to put something in the middle, I've got to move a bunch of stuff over to make space. And you guys will, we don't think too much about the memory models that we use in this class, but you guys will get more practice with that later. So there's some overhead to doing that that's sort of inherent. When you use higher level languages, MATLAB, Python, JavaScript, right? A bunch of higher level languages, they typically will present you with a list as a data structure. That's kind of the linear data structure that most of those languages support. And they don't really allow you to use an array even if you wanted to. Now, there are exceptions to this. So in Python, for example, there's a very popular library that's used to do numerical calculation that's called NumPy. And now we actually start to get to places where performance actually really matters. And so if you look at NumPy arrays, they're different than Python lists. Actually, they have more constraints associated with them that really have more to do with the fact that they're a little bit more like an array in a lower level language. Also, if you look at lower level languages, things like C, C++, Rust, Go, These languages typically have an array. They have an array that you can use. Some of them also have a list or some list implementation that you can use. C, I'm not sure. I mean, I'm sure there's some C library that provides a list, but built into the language. I know that Go provides something like a list that you can use. And I also know that C++, I'm sure, has some library to do this. But the idea is that these are languages that are designed for lower level programming. What we mean by that is programming where you're using a simpler set of abstractions, but is also typically a place where performance is more important. And so those languages might actually need to think about certain things that higher level languages don't have to bother with. And so those languages will typically have some notion of an array. As I pointed out in the past, Java is kind of in an interesting spot because it's a language that sort of straddles this weird divide where there are things about Java that sort of harken back to these lower level languages, like its support for arrays. But then there's also these higher level language features like garbage collection and things like that. And on some level, I think the reason for this is that Java is a very old higher level language. And so it still has these vestiges of support for stuff that things like, so again, Python kind of just said, we don't need to do arrays anymore. Who cares, right? I mean, we'll just do lists. They're more flexible. There's a performance penalty that you pay to use the Python list, and that can become a problem in certain cases. But in general, computers are powerful enough now that the flexibility and the speed and Python's a great language for kind of doing these small things and just getting them done quickly. It's like, I don't really care, if this is super fast because it doesn't have to be, right? I'm just writing a little tool to some of the things the guy talks about in coders, like these little small programming tasks. I mean, if it takes a second, it's fine. It's like no one cares. So yeah, I think that the support for something like an array is connected to, what the goals of the language are. Am I really going to use this language to do kind of low level programming where I need to control how things are laid out in memory at a very low level? Or is this the higher level language that's designed to trade off performance for, being able to get things done quicker? And so I think that's probably where the trade-off goes. MATLAB, for example, again, MATLAB is not a low-level programming language. It's a high-level, language designed to enable sort of numeric simulation and things like that. And so in MATLAB, it doesn't surprise me that there's no now again, the place where this gets interesting is supported for certain types of matrix and vector operations, right? In MATLAB, in Python, those are places where it can you can end up with big enough data sets that you actually care about the fact that things are a little bit more compact in memory. And so I don't remember exactly, but I think when you create like arrays in some of these libraries, they have a few more rules associated with them than a list would. It's a little harder to modify and things like that. You might have to specify the size up front, sort of the way you do with a Java array. And that's because internally, the data is being stored in a much more array-like fashion. So it really depends. I tend to think, when I think of the two most powerful data structures that I think people need to know in order to build useful things, it's lists, which we're talking about now, and then something called a map, which we'll get to soon. Those are the two most sort of powerful high-level data structures that are supported in a wide variety of programming languages and lend themselves really well to a wide variety of programming problems. Now, neither one of those is a particularly low-level abstraction. They're pretty high-level abstractions, but they're just so useful, right, that you find them. Python has them lists and dictionaries. JavaScript has them lists and anonymous objects. Go has them. I think Go has maps, and it has something called a slice, which is close to a list. So a lot of programming languages now come with these, batteries included. It's a good question. Can we go over the remove function? Yeah, of course. So, and this is like, I rarely actually want to be able to draw a picture of anything, but this is one of these places where it's somehow it might be a little bit easier to visualize. You might want to draw a picture yourself, right, to kind of figure out what's going on here. I don't even have any paper. I'm not a paper person. Well, hold on. Maybe I'll get. see if the Sharpie still works or not. Okay, so I'm going to draw this out here. Oh, look at that. Okay, it's kind of nice. So if you think about it, let me turn the camera on and make sure that you guys can see this. And probably what I should do is, there we go. Yeah, so here are my two arrays, right? I've got one array of size 5 and one array of size 4, and this is this is what I'm starting with. This is what I want to end up with. Right, so when I remove, the result, in this case, I'm starting with an array that has 5 values. The result's going to have 4 values. So, you know, then there's some value in here. It could be the first one, it could be the last one, it could be any of the middle ones that I'm going to omit, that I'm going to leave out. Okay, so let's kind of, and I'll pick one at random here. So in this case, I'm removing the item with index 1. And so this is the top, by the way. So this is 0, and then the indices go downwards. So if you think about what I need to do, I essentially need to copy everything from this array into my new smaller array, but I need to skip this index. And so the way that the solution sets things up is it uses 2 indices. One, and this is not the only way to do it, but I think it's probably the most clear. Let me make sure that this is still visible. Yeah. So I use one index for this array and a second index for this array. And they typically move along together because usually I'm just copying one over and then moving to the next item. But there's one place where this one goes forward and this one doesn't. And that's when I move around this element that I'm removing, right? So let's think about it at the beginning. So I start off, so the index I'm removing is 1. So I start off with both my indices at 0 and I copy from 0 into 0, right? So I do, right? Chunk. And then I get to 1, and that's the one I need to skip. This one should not be copied into the new array because if I do that, then I haven't removed it, right? So I skip this. So this index gets incremented twice, and this one only gets incremented once. So this one went from 0 to 1, and then I said, oh, I'm skipping this one. So I went to 2, and this one went from 0 to 1. And so now I'm going from 2 to 1, 3 to 2, 4 to 3. And then I'm done. Oh, sorry, let me hold this up so it's a little bit more visible. Yeah, look at that. Look at that beautiful diagram. Old school. I have a whiteboard I need to put together, probably now, actually, given that I'm starting to draw things with Sharpies on pieces of printer paper. So yeah, so the trick is, you know, this is kind of the picture that we need to maintain in our mind. This is what we're trying to do. This is one example for the case where I had an array of size 5 and I'm removing the element at index 1. But this is a general approach. And so now let's go back and actually look at the code that I'm going to use to do this. Right? And so this looks like this is the end here. Yeah. All right, so let's start at the beginning here. Okay, and so this is, you know, I had get and set already set up, and so here's so you know the first step is, right, I need to actually create this smaller array, right? So that's what I'm doing here on the first line. I'm creating the array with size 4. In this case, I started with size 5, going to size 4. Then I save a reference to this item because I need to return that. That's the semantics of remove. Remove hands back a reference to the object that's being removed from the array. So I grab a reference to this one. Then I set up my 2 indexes. So one of them is here. So I could actually set these up both inside the loop if we wanted to, but I don't know. This is more clear. So, you know, I have a new index. That's the index into the new array over here. And then I have my old index, I, which I could have called old index, but I'm just using I, that's here. And so you'll see, in general, I go through this loop and I'm kind of copying things from the one array to the other, but there's one time where this if condition will return false and I won't enter this block and I'll just go back to the top. That's the time where I bump I'm using I over here and new index over here, so I bump I past that value and new index just doesn't move. And so that's what takes I from 0 to 2, while new index only goes from 0 to 1. And once I've skipped that value, the rest of it just, is pretty straightforward to go through. Let's see here. Was this actually working at this point? Yeah, look at that. Oh, and I've got this. Let me try that. Okay, that's better. Yeah. So the, and that's the only trick to it, right? When you do add today, you're going to pursue a similar strategy, right? So, add, let's go through how add might work. I'll use the other side of this, right? So an add, and it's great because I can actually just draw into the outline of the other, right? So an add, the situation is reversed, where what I want, back and flip this around. So with add, what I have is I have a start array that's smaller than my end array. And I've also got a new item, right? So let's stick that new item up here, right? This is my new item. And then I have somewhere where I need to put that. So let's say that I'm putting the new item into index 2. So the third position in my new array. So I can do that whenever. I could even do that before I start the loop. Doesn't matter. But at some point, I need to set the end array to refer to that new item in the right position, right? So I'll set it, position index 2 here. And then I just copy everything else. So I still am going to need 2 indexes. And in this case, what I'm going to do is I'm just going to make sure that I skip this so I don't overwrite it. So now I copy from here to here, from here to here. Now I get here, I say, uh-oh, bump this one forward because I don't want to overwrite the new value, here to here, here to here. And that's how these 2 down here get pushed down 1. So they end up 1 index further in the new array. And so again, the approach is pretty simple. The code's going to look slightly different, but it's also going to look pretty similar, right? So instead of creating a slightly smaller array, I create a slightly larger array. Instead of pulling this out, I need to push something into that new array. I still maintain 2 indexes, and then what I do in here, I still need to handle that case where I'm at the index that I just inserted. I need to handle that a little bit differently. Most of the time, I'm just copying from the old array into the new larger array, but there's that one spot that I need to treat carefully. And so if you come back to remove, that should help things make sense. Good question. Let me go. Oh, sorry. Yeah, I meant to be showing you this. So instead of a slightly smaller array, use a slightly larger array. I need to put something new into that larger array. I still use 2 indexes, one for the new array and one for the old array, and I still have to handle that case where the index reaches the spot that I've added a little bit differently than I handle the other cases. But other than that, things should just work. Yeah. So by default, we remove the last one. No. There's no default here, right? I'm always removing the one so the remove always takes an index. And so I'm not, the one that I'm going to skip is the one with that index, right? And so remove can remove from anywhere. And if you look down here, you'll see that when we're testing it, we're removing this array, this list has size 3. I'm removing the item in the middle here, right? And I'm making sure it equals 2, and then I'm making sure the array got smaller by 1, the list got smaller by 1, and that the other 2 operations still work properly. So remove takes the location of the item to remove. And does that. So we should, if your remove works properly, it should be able to remove an item from anywhere in the list. Front, back, middle, doesn't matter. It's really the same code, right? There's really no need to handle any particular case in a special way. The same thing works. So, if it's the first item, then I just skip the first item. If it's the last item, then I skip the last item in the loop. Otherwise, somewhere in the middle, I skip that one. It's just, this will work for any valid index. And I know it's valid because I stuck this assertion right at the top, right? The other thing that trips people up with add, and I'll just give you a big hint because I know that people get stuck on this, is that when you add, the assertion's a little different, right? So when I remove, I have to remove something that's in the list, right? So the list index has to be valid. When I add, the list index actually doesn't have to be valid. Most of the time I'm adding somewhere into the list, but there's one spot that I'm allowed to add in a list that's not a current valid index. And so you have to tweak this assertion slightly. It's just a small change to it, but that tends to throw people off, right? So again, think about the case where I'm adding, but I'm adding down here, right? So let's say I'm adding in index 4. Is index 4 a valid index for my old array? No. The only valid indices are 0 through 3. So I need to handle that case a little bit differently. Yeah, it's a small change, but again, it tends to frustrate people. So we will do, we're going to do linked lists. That's the next thing, right? So now we're not going to reassign pointers because Java doesn't have pointers. We are going to reassign references because Java has references. And so yeah, the next implementation of a list that we will do will use linkage. We'll use references. So, one way to think about it is like, how does the list know where an item is? With an array, internally, I know where an item is because I'm using the array to keep the location. That's why get and set are so simple. But that's not the only way to do this. There's another approach. Another approach is that, I link every item to the next item. So every item in the list knows where the next item is. And if I do that, and I start, and I know where the beginning of the list is, then I can walk the list, which you guys will have a chance to do, to get to the right spot. And then I can return that value. So that's a different way of representing the information that's stored in a list. And it works just as well. I can implement the same interface that I implement here for my list that uses an array. The performance is different. The performance for some operations is better, and for other operations is worse. And so there's a trade-off between the two. That's one of the reasons why, Java, if you look at Java, it has a built-in array list. It also has a built-in linked list because, if an array list were always better, you would always use an array list, but it's not. There are applications where a linked list will outperform an array list. And so understanding the performance differences between the two lists will help you choose the right one for whatever you're trying to do. Yeah, good questions. Other questions about lists. So yeah, we're seeing a little bit behind the curtain here. And again, if you can find the actual Java source code for array list and for linked list, and you could look at those and you could see how it differs from what we're doing. I suspect particularly with array lists, they're probably doing they're probably playing some tricks that we're not playing. The problem with our implementation here is that every time I remove or add an object, I have to create this whole new array. And even just allocating the new array here takes time. So when I have to create a new array, I basically have to tell Java, okay, go find me some memory for this new array, and that can slow my program down. And so there's approaches to maintaining the array. So if you think about it, right now we're returning values not length, this is the size, but there's actually no reason to do that. I could maintain the size separately, and then I could only create a new array whenever I needed to, right? I could still move things around in the same way, but so here's one way to think about it. So, and this is actually, I think, more about how the array list implementation actually works. When you start off, you can actually give it an initial size, and it'll allocate an array for a certain number of elements, even if the list is empty. When you run out of space, it doesn't get an array that's one item bigger. It gets an array that's a lot bigger. So let's say your array stores 4 items. Your list starts out empty. You add items 0, 1, 2, and 3, and now it's like, oh, I need more space. But it doesn't go out and get an array of size 5, because it's like, whoa, hold on, because then I'll just have to go get one for size 6 and size 7, and I see where this is going. So it'll go out and it'll get an array of like size 32, or bigger than that, right? And that gives it room to grow, so it doesn't have to reallocate the array every time. It still has to move things around, right? That I can't get away from, but at least I don't have to go out and keep reallocating arrays over and over again. Then, so for example, I add 4 items, I get a much bigger array, then I add, the next 28 items, and now I get to 32, and it's like, oh gosh, this array is getting really big. Let's go out and get an array of size like 256 or something like that. It's quite a bit bigger. And so there's a trade-off here between Computer science is full of trade-offs, which is one of the things that's so much fun about it as a field. There's a trade-off between the amount of memory that the list takes up and the amount of times you have to allocate new arrays. Allocating new arrays is not free. That takes up that causes Java to have to do some work. Maintaining an array that has more space in it that you need is also wasteful, right? Because I've got extra memory. It turns out today, I mean, memory is pretty abundant in a lot of our programs. And so the idea of having a list that's wasting some memory so that it doesn't have to run the allocator as often is not a bad trade-off. And that's typically what these implementations will do. I don't know exactly, how they figure it out, whether it's powers of 2 or in some other way, but that's usually what they'll do. And then same thing in the other direction, right? So, let's say I have an array of size 256 and you remove 10 elements. The array, the implementation is not going to be like, okay, well, I'll allocate a new array of size 246. It's like, nope. I'm going to keep this space here because I might need it. Because the next thing you might do is add 8 elements. And so if I keep the array I already have, then I don't have to run back and immediately reallocate something. So essentially, when the array gets bigger, it typically tends to over-allocate. And when the array gets smaller, it'll wait, right? Eventually, let's say you create an array of size, some huge capacity, and then let's say you have a list and you add 1 million elements to it, and then you remove, 1 million minus 1 elements from it. At some point, it's going to be like, okay, I've got way too much space, so I'll hand this back and I'll allocate a new array that's smaller. But it typically tends to be very conservative about doing that. Part of this is, so our implementation is essentially optimized for consuming as little memory as possible. Our implementation never wastes memory. So if you have a list of size n, we have an array of size n. That's not how the real implementation would work, right? In the real implementation, if you have a list of size n, you typically have an array that's bigger than that, right? In our case, our array is always the exactly right size for the number of elements. The trade-off is that every single time you call remove, I have to allocate a new array, and that allocation is expensive. So that's the trade-off here. Again, let's see here. Let me pull up the actual array list implementation, and we can check it out. Array list Java implementation source code. Blanc. This is from the Open JDK. This is an open source implementation of Java. And let's look at the add function. Let's see. So so check this out. There's this private method here called ensure capacity internal. Let's look at that. So what this is going to do, I bet, right? Ensure explicit capacity. Oh Lord. Okay. I don't know why they've done this way. Wow. Sweet. Yeah, I'm sure the person who... okay, here we go. It looks like this is... Wow. Okay, I'd have to actually read this a little bit more carefully to try to figure out what's going on here. But I think what it's actually doing is increasing this in powers of 2. I don't know if there's actual way to get the capacity. Let's see if we can figure that out. Let's see, Java array list get capacity. It doesn't look like this is possible. Yeah, it looks like I could hunt this down. I don't think I don't think we're gonna be able to do this in the playground, but anyway, yeah, there's so there's this internal. So essentially, there's 2 different things, right? There's this internal capacity that's the size of the array that the list is actually allocated, and then there's the size which is exposed to you. So with a little bit of poking around, we could figure this out, right? We could actually get the array list implementation to cough up its actual internal size, but it's probably not worth doing. But anyway, if you look at the code there, what it's doing is it's over allocating, right? It's saying, okay, the array went from you added 1 item, but it's actually going to go allocate a much larger array. And what that means is that the next 1, 2, 3, 4, n times you actually add things, it doesn't have to allocate. So it's better in general to do more allocations and have them and waste some space than it is to do, fewer allocations and waste some space along the way than doing more allocations and having the space be exactly the right size. Our implementation does more allocations, but the array is always the exact right size. And that's what we'll ask you to do in add as well. Is the runtime for both add and remove on or o1 in best case? No, so this is always going to be, let's look at, so whenever we think about best case, worst case performance, we want to look and see if there's any dependence on the input at all, right? So do you see any break in here? Or any type of, way for this loop to act and execute? No, so this loop will always execute values.length times, or values is the size of the array. So this is on. So people get a little confused about this because they'll think, well, if the array is size 1, then it's o1, but that's not, o1 is really constant. It means that no matter how large the array gets, it's always the same amount of time. So it's maybe a better way to think about it as o constant rather than o1, although you'll hear people use both terms. On means that there's a dependence now on some feature of the problem, which in this case is the length of the array. So as the array gets bigger and bigger and bigger, this remove method is going to take longer and longer and longer and longer. And actually, since we have a few minutes, why don't we actually try to show this? So what I need to do is I need to create. I'm going to write a method to create an array of a given size, and I'll just fill it with some random data. So we'll have this method return an array of integers, and I'll take a size, and I'll say for I is 0, I is less than size, I plus plus. Oh, I need to allocate the array first. Integer. I'm using capital I integers here, so that I can pass this to my simple array list constructor. So new integer. So this is that wrapper class for ints. You'll see I can just store it right in there. Values I is equal to, do I have random? Nope. I'm going to import random. Import util.random. So I'll say random is equal to new random. I'm not even sure I have to do this, but it's just fun to use random. Next int, okay? And then I'll return values. All right, so what I've done here is I've created a function that's going to create random arrays for me. And let's just make sure that this works. So we'll say assert create array 1024 dot length is equal to 1024 and oh, it doesn't like this. Why not? Oh, it's not in scope, right? Okay, let's put it in here. Okay, great. So now the question is, how long does remove take, right? And so now what we're going to do is I'm going to say object values is equal to, so this will create an array of size 1024, and then I'm going to remove. Now for timing measurements, we did this a little bit yesterday. We're going to use this system.getNanos. So I'm going to say long start is equal to system.getNanos. I'm not even sure if this returns nanoseconds, but this is the most precise timer that we have available to us. Then I'm going to say values.remove, and let's just remove something at the beginning. And then we'll say long end is equal to system.getNanos. System.getNano. Oh, sorry, get nanos, Java. What is it called? Nanotime, sorry. Nanotime. It's nanotime. Nanotime. Okay. Great. Why? Oh, I need to create the list. And so I'll say, what is this called again? Simple array list. Simple array list. List is equal to new list. Simple array list, and I'll pass it values. And then I need to call list.remove. Okay, great. And so now I'm going to print the difference between these. Okay, so it's about, I mean, this will bounce around a little bit. You're running this on a real machine as part of our playground. So sometimes there's other tasks running on that machine, sometimes there isn't, but you'll see, we're never getting lower than about 42,000 here. Now let's make the array bigger. And you can see, this didn't go up quite exactly a factor of 10, but we definitely added a 0. Now let's make it bigger, and you'll see we've added another 0. And so this remove function, because it has to do this array copy, is taking longer and longer and longer, right? If I make the list really small, like have it be 32 items, now it's really, really short, right? If I make it bigger, now it's taking, and again, these are estimates, right? Because there's a lot of noise in this calculation. If you wanted to do this for real, you might run it like 100 times and average the results or something like that. We can't do that here because every time we remove, the list gets smaller. So we're kind of changing the number. If the list was big enough, it wouldn't have that big of an impact, right? So if I make a really big list here, that's not going to matter very much. But you can see that as we add more and more and more elements to this list, that remove method is getting slower and slower and slower. And if we plotted this out, we would expect to see a curve that's roughly linear. Yeah, so again, let's be careful here. There's no best or worst case here. It's always ON. If the length of the list is 1, then it might be a 1, but that doesn't make it a 1, right? It makes it ON. And yeah, I think that's an important distinction to draw here that I'll probably try to clarify because I see where this confusion is coming from. Best case has to do not with N. Best case has to do with some other feature of the input, right? So we have some algorithms that, in general, if you give them lots and lots and lots of inputs are, ON, but there are certain inputs for which they're O1. In this case, there's no special input here, right? So for example, if I was searching for something, or there's certain features of a problem sometimes that will cause things to perform better or worse. In this case, this is always ON. If N is 1, that doesn't make it a 1. That's still ON, because if I make N 1024, then it gets 1024 times slower, and so I see the dependence. Yeah, it's a good question, and we'll try to clarify this over the next couple of lessons. All right, I think we're in good shape. Any final questions before we... So tomorrow, we're going to look at a completely different, so between tomorrow and Friday, we're essentially going to tackle a completely different approach to implementing lists, which is cool and different and brings in some of the things that we just learned about object-oriented programming, including references, and we'll actually get to see a new feature of Java, which is inner classes, which is pretty neat, and this will be fun. Next couple days, that's what we'll be doing, and then we'll spend some time comparing the performance and seeing kind of what the trade-offs are and stuff like that. So this is a lot of fun. I'll look forward to seeing you all tomorrow.